Hi everyone, welcome back to the course on understanding RAG. Today we're going to be talking about efficient retrieval. But what is efficiency, first of all? This is actually a hot topic right now in the context of how AI is being developed. So far we kind of have chosen the easy direction, the brute force path with large language models that basically can predict the next word in a smarter and smarter ways, but at what cost? Large language models, foundation models in general, we know that they consume a lot of energy, they need a lot of water for cooling, and they also require a lot of space, right? So some are looking into building a more efficient kind of AI where we take a more neurosymbolic approach and we try to be more efficient in the types and amount of resources that we use. So this is also related to what we discussed in the previous course of natural language understanding. But this is truly becoming an issue today for the impact that those AI and data centers have on the environment. Also, in terms of the heat that they produce, they are literally changing the ecosystems around them. And this is also interesting in terms of how intelligence has evolved. So this is also something we discussed in the previous course. The human brain is not only amazing for the things that it can do, but also the fact that it can do all those things in a pretty limited space and by using very little energy. But okay, what is efficiency in the context of information retrieval? It can be efficiency in terms of speed, first of all. How long does it take for me to answer a user query? How much it costs me to maintain and host my information retrieval system, and so on. So we've actually talked a bit about efficiency already in lecture one. Remember, we talked about skip pointers, dictionary and posting compression, blocking, front coding. So in this lecture, we're going to be focusing on three more optimization techniques that we use to build a more efficient retrieval. The first is text categorization, which aims to increase the accuracy of the system. Then we have spell correction, which is about increasing the robustness of our systems. And finally, query optimization, which is more about increasing the speed of the system. So text categorization can be useful for many different reasons. For example, if I have a query apple, if I then have different categories for this apple, like tech versus fruit, I can then reduce the search space and only look for the query in the documents that are supposedly about tech or fruits, depending on the context of the user query search. And then it has a lot of other benefits because in general, if I can segregate my document collection in different categories, then I can optimize my document structure and also the models that I have for these documents that then I can use at query time. So what is text categorization? Simply given a set of documents, being able to assign them to a different class. So I can have a binary classification problem when I only have two class or even one class. So I have to classify documents as belonging to the class or not, or I can have multiple classes. So these are things that we briefly also discuss in some parts of the course already. But let's give a more practical example. Let's say that my classifier is about classifying emails as spam versus non-spam. So I'll have some training data that tells me which ones are the good emails and which ones are the bad ones. I will do some feature extraction again because I don't want to work directly on the document. I want to work on some representation, some model of the documents like we have done in lecture 1 and 2. Finally, I'll be using some classification algorithms to decide whether a new email is spam or not spam. So when at testing phase, when I have to classify a new piece of data as belonging to the class or not, I will have to do a similar feature extraction, use the classifier model that will tell me whether this new email, new document belongs to the class or not. So in this course, we're going to make things simple and assume that each document only belongs to one class, but in fact, in real world cases, things may be slightly more complicated. Same document may belong to more than one class, and also you may have a hierarchy of classes. So we're going to be using probability. So let's do a 1-minute crash course on probability. What is a probability? Simply counting how many times you have an occurrence like the King of Hearts versus the total deck. So the King of Hearts has a probability of 1 on 52 to be picked out of the card deck. While if I'm just calculating the probability of a king to be selected, there are 4. So I have 1 or out of 13 probability to pick a king. So why do we need probabilities? Because that's how we can do classification using the naive Bayes classifier that we also mentioned in the first course. So, but before we do that, it's important to define conditional probability. So one thing is the probability of A and B. Another thing is the probability of A given B. So this is an important probability to calculate because it tells me what is the probability of an event A to happen given that B has happened. So this could be seen as the probability of people to have an umbrella with them given that it's raining outside, which is different from the probability of that it's going to rain if people bring out umbrellas. So it's important not to be confused by these two different things. So one thing is the probability of being an assistant professor, given that we are looking at someone in their 50s. And another thing is the probability of someone being in their 50s, given that there are an assistant professor. So don't get confused by this. But this is important because then we're going to be using the Bayes rules for classification. So C is the class that we need to take into account for classifying our document D, and this is exactly what we need to do. We need to decide what is the probability of a document to belong to a class, so the probability of C given document D. So this normally is a complicated probability to calculate, but thanks to the Bayes rule, we can use these other 3 probabilities, which are much easier to calculate. So I need to calculate the class. I need to take the maximum of the probability of C, the class, given the document. So the document for now, we represent it just as a bag of words. All these X1 to N are the words that make up the document. So this is the probability that I'm after. Given the documents, given the words that make up the document, decide which class this document belongs to. I can use the Bayes rule to replace this very difficult probability with this one. And then, since I'm looking for a max, I can ignore the denominator. So why is this? First of all, why am I looking for a max? Because eventually I'm going to be left with 2 probabilities, the probability of document D to belong to class C and the probability of document D to not belong to class C. Which one do I take? The maximum one, right? That's why I'm looking for a max. And that's also why I can ignore the denominator, because then I'm just looking for the biggest probability among these 2. So I'm only left with these 2 probabilities to calculate. Let's start with the easy one, PC. What is PC? Is the probability of the class. Very simply, is the number of documents that belong to class C in the training set divided by the total number of documents. So if I have a situation like this, This is my training set, and this is the document that I need to decide whether it belongs or not to class C. In this case, we take class C as class China. So this is a typical example of binary classification where we need to decide whether the document belongs to a class or not. So PC is what? Is 3 out of 4, because 3 documents out of 4 belong to class C. What is the P of not C is 1 minus the probability of C. In this case, 1/4, because only one document does not belong to class C. So to continue, we need to break this probability down into smaller probabilities. So I can convert this into the single probability of each word given class C. But in order to do this, I need to make a very strong assumption. I need to assume that all these words are actually independent from each other, which is not really true in most cases. So there will always be some correlation between different words in a document. But to be able to continue, because I don't have any way of calculating this probability, I assume the independence of all these words so that I can break down this probability. I can factorize it into these smaller probabilities that indeed I can calculate. Because what are these? I'm just counting how many times each word in the training set belongs to class C. So again, these small probabilities, I can also calculate them easily. They are the number of times that each word appears in the documents that belongs to class C, divided by the total number of times that terms appears in all the documents that belongs to class C. So before showing you how this works with an example, I need to do a little bit of trick first. Why? Because the big problem with this factorization is that even just one of these is 0, the whole thing will go to 0. So in order to prevent this, I define each of these as I defined before, but I do a +1 at the numerator and plus k, the size of the vocabulary, at the denominator. So this will prevent me from having any 0 in that factorization, so that those words that don't appear basically will go to probability 1. So when I multiply by 1, nothing happens, right? So to conclude, this is what we did. We need to calculate this probability and take the maximum to decide whether document D belongs or not to class C. So we use the Bayes rules to then come up with only these 2 probabilities that I need to calculate. And we also added this trick to avoid the 0 probability. So at learning phase, I'm just counting how many times words appear in the class, and then at testing phase, I just multiply those probabilities all together. So it's very fast. I just take the probabilities that I calculate earlier at training phase and multiply them all together to decide whether document D belongs or not to class C. So let's see this with an example. Here we have document 5 is a new document that we need to classify as yes or no. Does it belong to class China or not? How do we do that? We will have to calculate 2 probabilities, the probability of document 5 to belong to class C, the probability of document 5 to not belong to class C, and then take the biggest. In order to do that, we need to calculate all these prior probabilities. So first of all, our vocabulary size V is 6 because we have 6 different words in our vocabulary. Then the probability of the class, as we calculated earlier, is 3 out of 4, and not C is 1 out of 4. Then I just have to calculate all these other probabilities. So for example, the probability of the word Chinese to belong to class C is 5, because I have the word Chinese 5 times in all the documents that are belonging to the class China, divided by 8, because that's the total number of words in the documents that belong to class China. And then, as I mentioned earlier, I do +1 and plus K, which is the total number of words in my vocabulary. So I calculate this the 3/7, and then I have to do the same for the probability of the Chinese word not to belong to class C. In this case, it only appears once, divided by 3, because I have 3 words in this only document that doesn't belong to class C. And this is how I calculate my probability. So I'm learning from the training data set that I have what are the probabilities of each word to belong or not to each class. So this, no matter how long it takes, it's done at training phase. It's not eating out into any time of the user. Then at user time, all I have to do is to take these probabilities that I've pre-calculated and do a multiplication. So I have to take the probabilities of these 3 words, Japan, Chinese, and Tokyo, and calculate the probability of them to belong to class C and not. So in this case, I take the probability of Japan C multiplied by Chinese given C 3 times, because the word Chinese appears 3 times, multiplied by the probability of Tokyo to belong to class C. So when I multiply all these quantities together, I get this number. Then I have to do the same for not belonging to class C, which is this other number. And since the first one is bigger, then the final answer is yes, document 5 does belong to class C. So don't forget this. If a word appears 3 times, then you have to use that 3 times. That's an important bit of information for naive Bayes classification. Now let's go to the next optimization technique, which is spell correction. This is quite important because then I need to decide, first of all, whether I want to correct any misspellings in my documents, but most importantly, how to handle misspellings in the query. Do I want to reformulate the query, for example, if the user misspells the query? And there are a lot of benefits that come with spell correction. So we're going to see how to perform spell correction. And it is a very important thing to have in your system, because then misspellings happen all the times. So the easy approach that we can take to spelling correction is when we have a misspelling that results in a word that is not an English word. So in that case, it's very easy to know that we have to implement spell correction. In some other case, it can be more tricky, because if the misspelling results in a word that is also in the English dictionary or in my dictionary, in my information retrieval system, then things get slightly more complicated. But before we get there, we need to define how to calculate the distance between 2 words, right? If I have a misspelled word, how do I choose which word to replace it with? And that can be tricky depending on what my input system is. So if we are taking input through a QWERTY keyboard, I can expect different kinds of misspellings, for example, due to the fact that O and I are near in a QWERTY keyboard, so they are more likely to be swapped. But then if I'm talking about OCR, like handwritten text, then you have different problems. RN can pass as an M. And if I'm talking about speech, there are words that are written differently but sound the same, like right versus right. And then we have to decide what to do. Once we detect a misspelling, what do we do with it? Do we automatically correct it, or do we ask the user, did you mean this or that? So we're going to see a few simple techniques to calculate the distance between words. So assuming that I get a misspelled query, I need to decide what to replace it with. And this is an important concept because it teaches us how to define the distance or the similarity between 2 words. So this is slightly different from what we have defined when we talk about cosine similarity and TF-IDF score, because earlier we were talking about whole document and the words that make up these documents. Now we are actually looking at words letter by letter. So the edit distance is basically looking at two words and looking at how many operations I need to do to go from a word to another. So for example, if I get the query dove and I don't have dove in my dictionary, I'm gonna go and look for the word in my dictionary that is most similar to dove, which is the word that has a smaller edit distance with dove. In this case, dog, because I only had to change one letter. Similarly, the edit distance between cat and act is 2 because I have to transpose two letters. And between cat and dog is 3. They're completely different because they're made of completely different letters. So this is a good example to understand that the kind of distance or similarity that we are calculating is purely syntactical. We are not talking about semantics because then in that sense, cat and dog are very similar because they're both pets and they're both animals. So there are different ways of doing this, especially if you are using Python to do this kind of operations, but I'm going to teach you a way to also do this with pen and paper. We're going to look at the Levenshtein distance. So this is the formula. I'm calculating letter by letter what is the cost of going from one word to another. So let's take these two letters, fast and cats. I put them in a matrix. I can put fast on the rows and cats on the columns, or vice versa. And then I index them in with 4 numbers, the numbers that make up the number of letters. So this just happens to be a square matrix, but you can also have fat or tall matrices. Doesn't matter. You can still calculate the Levenshtein distance when you have two words that are made up of a different number of letters. So the way it works is that I slowly fill in all these blanks by looking at the top left corner, the neighboring numbers that I have here. So whenever the two letters are different, I just take these 3 numbers, I take the minimum number and I do +1. So I look at the minimum and I +1. Why? Because this comes at the cost. I need to go from letter F to C. So the same I do here. The minimum of this 3 is 1, +1, 2. And same here, 2 + 1, 3. 3 + 1, 4. Same I do here. And now look, A is the same. So this comes at no cost, so I don't have to do any operation. I just bring down whatever number I have on the top left corner. So here I put 1. But then next A is different from S, so I still do the same as before. The minimum is 1 + 1, 2. Minimum is 2 + 1, 3. Then I continue until I once again encounter the same letter. So I just bring down this 2 here. And then same here until I encounter the same letter S, I just bring down the 2 here. And finally, the minimum 2 + 1, 3. This is the final result. The Levenshtein distance between fast and cats is 3, which tells me that maybe cats is not a good replacement for fast, right? I would want to maybe, if it's misspelling correction that I'm doing, then I would want to maybe replace fast with a word with the Levenshtein distance 1. So again, I can weight the different errors that I expect the user to do based on what kind of keyboard he or she is using, or whether I'm looking at handwritten text and so on. An important question is when to perform this kind of operation. It would be very costly to do it all the times, right? So maybe I only do it if I get no results. So if I get some result, I assume that the query is not misspelled. If I get 0 result, then maybe I can calculate the Levenshtein distance and try to do some replacement. But what's another faster or smarter way to do this? Because Levenshtein distance, as we saw, it takes some time because I have to go through each pair of words letter by letter, right? So another option is to use the Jacquard coefficient, and we'll do that by splitting words into n-grams. So instead of looking at words letter by letter, I will look at maybe bigrams or trigrams. So this is not so different from the by-word trick that we were using earlier for indexing. So here, for example, I use a trigram, a three-letter window to slide through every word, and then I calculate the overlap between these two. So each of these two words, November and December, are made up of 6 trigrams, and they share 3 of them. So there is a half similarity, a 50% Jacquard similarity between these two. So Jacquard is also something that we mentioned in the past lecture when we mentioned about coming up with the score between 0 and 1. Eventually, we didn't choose Jacquard in that case, but in this case, it's a good coefficient to use. How to define that? Very simply is the intersection between two sets divided by the union. So let's see that with an example. Let's say that I have these two vectors. Object A is 1, 1, 1, 1. Object B is 0, 1, 0, 0. How do we calculate the Jacquard coefficient? The Jacquard coefficient is given by the total number of commonalities, in this case 1, 1. There's only one coordinate for which I have 1, 1, so this M11 will be 1 divided by the rest of the coordinates. So the Jacquard coefficient in this case is 1 out of 4 or 25, 0.25 or 25%. And the distance is 1 minus the Jacquard coefficient. So this is similar to what we discussed in the past lecture. Cosine similarity tells me about the similarity. Euclidean distance tells me about the dissimilarity. So here we have the same. The Jacquard coefficient tells me about how similar two sets or objects or data points or vectors are. The Jacquard distance tells me how dissimilar they are. So this was good for those kind of spelling corrections that are not contextual. For the contextual one, I will need something different. I will need some deep learning algorithm or even a large language model that is able to model, for example, what word comes after which other word, so that I know that, for example, every time I have the word fly, it's very likely that the next word is going to be from rather than form. So it's still a matter of probability, but it's slightly more complicated than Levenshtein distance and Jacquard coefficient, because I need to model the context. But this is far from easy, because as we know and as we discussed in the previous course, we have the problem of multiple senses as well. So fly, for example, is not just a verb. It means a different thing as a noun, and then yet another thing as an adjective. So there are several issues with spell correction. So you have all these context-dependent things that you need to do. And also, as we mentioned, the big question is when to do spell correction. I don't have the luxury to do it all the time, so otherwise I will take away a lot of time from the user. And last but not least, sometimes by doing spell correction, I may actually get bad results, because let's say that the user is searching for bed to like improve his or her sleep, but then if I don't have the word bed in my dictionary and then I do spell correction, I may replace it with bad, because bad, B-A-D, is added distance 1, but then maybe that's not what the user meant. So I need to also be able to handle this kind of exceptions. Okay, we're almost done. We only left with the last optimization technique, which is about speed, making my system faster. And this is an important question because every time I receive a query, according to what we discussed in the previous lecture, I'm supposed to calculate the TF-IDF score between this query and all my documents, right? That's how I do the ranking. But imagine that I have 1 million documents. That means that every time I receive a query, I have to calculate 1 million TF-IDF scores. Now, that, of course, would take a lot of time, right? So optimized cosine ranking tries to answer the question, can we do that faster? Can we, instead of calculating the TF-IDF score between query and all documents, just select a subset of documents and only calculate the TF-IDF score of those top K largest cosine values? So this actually is like a K nearest neighbor problem, right? If I had the luxury to be able to visualize my documents and where the query ends up, then I could easily do this by just taking the documents that are nearby in the same region of my multidimensional vector space to the query. But actually, if I have a very big multidimensional space, it's not very easy to do that. And that's why I'm coming up with some tricks. Specifically, these 4 tricks: index elimination, champions lists, static quality scores, and cluster pruning. So index elimination comes from the simple idea that, for example, if I have a query cats, uh, it doesn't make sense for me to go and calculate the TF-IDF score between this query and those documents that don't even contain the word cats, right? So if I take this one step further, I only want to consider the documents with high IDF query terms and only the documents that contain many query terms. Let's look at these 2 separately. So the first one means that I only focus on high IDF. High IDF means what? Again, if you don't remember what IDF is, look at lecture 2. High IDF corresponds to low DF, so fewer document that contains the word at least once. So that means that these are rare terms. So this is a way for me to focus on the documents that contain the rarer terms. And finally, this is also kind of a heuristic. I only consider the documents that contain at least 3 out of 4, assuming that my query is made of 4 terms. I only look at the documents that contains at least 3. So what does it mean? If I have multiple word queries, I only look at the documents that at least contain a few of these terms. So in a situation like this here, let's say that the query is Antony, Brutus, Caesar, Calpurnia, then I only calculate the TF-IDF score between Q and document 8, 16, and 32. Why? Because this contains at least 3 of the 4 document terms. Why do I do this? Because I already know for sure that the other documents will definitely have a lower TF-IDF score. So why bother? I just focus on the documents that have a higher chance to have high TF-IDF scores. So along these lines, I can also come up with some champions list. What is a champions list? Uh, Before I even receive a query, I can build a champions list that tells me, given a term auto, what are the documents that are best in terms of TF-IDF score. So this sounds like I'm wasting a lot of time to do all this for every single word, but actually it doesn't matter because I'm doing it before I receive any query from the user. So it's important to be fast at query processing once I receive the query, but all the calculations that I do a priori beforehand actually doesn't matter how long it takes. So it's totally smart to do this. For every term in my dictionary, I calculate a ranked champions list that tells me what are the best documents to consider in case I get one of these terms in the query. And so the good thing about this, if the query just happens to be really auto, I already have the result there, right, in my champions list. If I have a mix of these, like if let's say the query is best car, I already know that I should look into the documents that are both in the champions list of best and in the champion list of car. Another thing that I can do is to come up with some static quality scores. So for example, if I'm looking for something in my document collection, as the top result, of course, I want to get the most relevant one in terms of TF-IDF score, but I would also want to have the top values, as the top documents, the ones that come from reputable sources. So if I'm searching for something in news articles, for example, I would want to have at the top the ones that maybe come from CNN or BBC rather than some unknown news source, right? How can I do that? By coming up with a sort of score, static quality score, that goes once again from 0 to 1 and that I can call G, that tells me how good is the source of this document. So this can be anything from a news source, or for example, if I'm looking at scientific articles, 0 can be an article that has never been cited, while 1 is a paper that has been cited most times, or it can be calculated in terms of how many followers a Twitter account has, and so on. So this is a quality score. You decide how to define it, but still important that you keep it between 0 and 1. So once you have this, which will be static for each document, it will not change based on the query. It will be a quality score that stays with the document. Then I can come up with the new score that I call net score, which is given by G, the G score, the static quality score, plus the cosine similarity between Q and D. So now I can use this net score to recalculate the champion list, for example. Again, this can be very good because I don't just present to the user the relevant documents based on the actual ranking calculated on TF-IDF, but also taking into account how reputable that document is. Okay, the last thing to check is cluster pruning, which is also a very smart way of reducing the number of cosine similarity that we are calculating. So the first thing to do is to decide how many leaders I want to choose in my document collection, and also the distribution of these leaders, so that whenever a query comes, instead of calculating the cosine similarity between the query and all the documents, I only calculate it between the leaders and then go on and calculate it for the rest of the items that belong to the cluster of the leader. So again, we are not covering clustering in this course, but let's assume that I have a way to define a leader for each document cluster in my multidimensional vector space. And this can be also done by categorization. For example, if I realize that I have 5 different classes, 5 different categories of documents, like tech versus animals versus fruits and so on, I choose a leader, a representative document for each class or cluster. And then whenever I receive a query, supposedly I should calculate once again the similarity between this query and all documents. Instead, I only calculate the similarity between query Q and the 5 leaders. Then once I realize which is the closest leader, then I go on and calculate the rest of the cosine similarity between the query and the rest of the items that belong to that cluster. So in that way, I ensure that I'm only looking at the documents with the highest cosine similarity and get a good ranking without having to calculate all the cosine similarity between query and all documents. Okay, that's all for this lecture. I hope things were clear. Let me know if you have any doubts or questions, and see you at the next lecture. Ciao.